Yeah, but this design didn't actually say instructions. So I don't know. That was kind of like more of a intuition. Yeah.
Okay, everyone. So today we have to move a little faster because time is running out, and we have to cover two things. So quickly finish the fork system call, which we were discussing last time, and move to the probably one of the most exciting lectures in this classes, which is about the context switch, essentially how you switch between the processes. So here, just a quick recap. So this is where we were left last time. So we said, okay, we are doing the exact system call. We created the new address space. Remember, exact replaces the address space of a process with a new process with a new binary, and it starts executing this binary from the entry point, right? So what we were doing, we allocated the kernel part of the address space, right? Because we want to have the kernel mapped in the address space because we're preparing the new address space for this the new process. We allocated the user part of the address space as well, right? And we loaded this user part of the address space from file, right? Because we said, okay, we're going to open this file, which user passes an argument to the exec system call. We see that it's an L file, and we do this program header loop, essentially loading every part of the file into the memory. And as we load, we first allocate new pages, and then load the text and data sections from the file into those pages, right? Do we remember this? Okay, and then we said, okay, we're almost ready to run. So, but the user program needs a stack to run, right? And so we said, okay, let's allocate the program stack. So, and I was telling you that, okay, we first we'll allocate two pages. One is the stack itself, and another is a guard page, right? And the guard page, what we do with the guard page is that we clear the user accessible bit. So essentially, if the user code tries, if the stack overflows into the guard and the user tries to access this page, the page is present in the page table, but instead of being green, this page is marked as yellow because it's yellow means no user accessible bit. And at this point, the system reports either a protection violation or a page fault, and the operating system reacts to it saying, okay, it's probably something wrong is happening, and typically kills the process, right? And I mean, kill is a little bit outdated terminology, but this is how people used to call termination of a process, right? So which you might think is a little abusive, the word itself. But okay, so we're good on that, right? Okay, so we created the stack, and we briefly discussed, again, we want to run some program. And obviously, we want to pass some arguments to this program, right? And so we said, okay, we will push these program arguments on the stack. We already have the stack page. We said, okay, there's this Unix or POSIX POSIX convention that if you invoke the program with two arguments, hello and world, the way the arguments will be passed, they will be passed as strings. So you cannot pass an integer, because you're passing those arguments from a shell. So this is essentially invocation from a shell, right? So you typed it as a user, you click a button, you click enter, the shell reacts to it, right? And later on, the program receives the two arguments and the name of the program itself, right? As an array of pointers to strings, right? And the second argument, argc, essentially says, this is the size of this array, right? And someone was telling me that there must be the last element of this array, which is 0. Let's double check in a second. I still don't know, right? But so essentially, if you want to pass an integer to your program, you still type a number, and then inside your program, you have to parse this number, saying, okay, it's 10, so it means 10, so it's an integer 10, right? That's how we create programs. Okay, cool. So, and this is essentially what x86 is doing. It will allocate space on the stack first for each of these strings itself. So here it's my program, dog, cat, frog. So space for dog, for cat, and a frog. Put them on a stack, then allocate space for this array itself on a stack. Put the array on a stack, connect those pointers correctly, and then will push the argc on a stack with a correct value, right? Just because to follow the calling convention, that main takes two arguments, argc and this argv array, right? Is that clear? Is this clear? Yeah. Okay, cool. And this is what exactly x86 is doing, right? So the code gets a little bit complicated, but again, if you stir it for a little bit, right? So it just says, okay, I will allocate all these elements on the stack. We'll configure everything correctly. Use stack is an array which represents the user stack. So we're not going to spend a lot of time here, but okay, as your homework, next homework, not this one, not the syscall, but the next one, you will be asked to create a new thread of execution, right? Which means that right now, the way I explain it, so this fork, we have fork and exec, but there is no way to create a new thread. So there's no way to run two threads in one address space, right? But the homework will ask you to do that. So you will have to pass some arguments on the stack for that thread create function, right? So this is why it's kind of important, but it will be much easier. So typically thread create will be something very, very simple. So it will just take a void pointer as an argument. So probably you will have just to push one thing on a stack, just one pointer. Okay, so, and this is where we stopped last time, right? I ran out of time. And now I say we have to switch the page tables. So what do you think I mean by that? What needs to happen at this point? Right, so we have to move from the old page table directory to the new one, right? Imagine this was your address space, the old one, right? From this old one, you did the interrupt. You landed on a kernel, right? You were executing in a kernel, right? And what we've done inside the kernel, we created a new address space. This one, for example, if this one was shell, for example, and shell created, let's say, ls, this is the address space for ls. It has a text section of ls, it has a data section, and it has a stack, right, of ls, for example. Agree with this? Our goal since this was like exec system call, which we say like, okay, let's say bin ls, for example, is to start executing ls from its entry point, which in case of x86 is just the main function. Agree with this? And right now we're sitting in a kernel right here. This is where we are inside the sysexec function, which implements this system call, exec system call. And the CR3 is still currently pointing to the address space, to the old address space, essentially the page table which describes this address space. But we created a new page table. We created a new page table which describes this address space. So logically, you want to switch CR3 to point here. Agree with this? Right. So we can start executing the new program. And what are we going to do with the old one? Right. Do we need it at all?
Because in case of exec error, then we need to return the value from child to parent.
Yeah, in case of error, remember there was this go to bad, and this go to bad will take care of the error and says, okay, we will probably deallocate this new address space. Everything what we created should be like wiped out, right? Because we're not going to use it. And then we will just simply return here with an error, right? But in case we don't encounter an error, then what happens? No, we start executing here, right?
We should beat the old page table.
Agree. So we should deallocate this old address space because we will never use it again. It's not the most efficient implementation of exec. you might think of, okay, why do we even like create a new one and throw the old one? Can't we just simply, load ls in the old address space? Can we load it here? Like a text section and a data section of ls, for example. Why not? No hassle, no need to create a new address space. Can we? We can. So, but what can go wrong?
We want to run parallel.
Someone works for HPC. No, like again, what happens if you loaded ls, just essentially, like I said, okay, like I loaded, let me change the color here for a second. You said, okay, I loaded the text section of ls and the data section of ls, and then suddenly, you know, like your memory allocator, you're about to start allocating stack, and suddenly allocator returns null. Gosh, it's an error, so you have to go to bed. In order to go to bed, you have to return here, but there is no here anymore because now it's ls, right? So error handling becomes complicated up to the point that maybe it's not even possible easily, right? You can save some state, you know, you can restore it back, but it becomes hairy, right? So that's why people don't do this. And essentially you say, wow, we'll create a new address space, and up to the last point, we will keep that old one around. And when we know that there will be no error at this point, we can deallocate the old one, right? Is that clear? That's why it's designed this way, right? Clear?
But while executing the program of ls, when we might see an error, right? So in that case,
While executing ls?
In the new program, let's say we are running the ls program and we have some null pointer exception.
Yeah, then you will like kill ls later on.
But we have written that status of that new process to old one. Right?
No. Remember the semantics of the exec system call. If it succeeds, you never see the old program again. If it's a fork, and fork will be implemented very, very similar to this exec, right? And I will assign it as a, this week there will be a quiz about fork. I will assign fork, and then you say, look, there will be two instances, right? And the parent will get an error code, like not the error code, but the ID of a child. But if child gets an error, then the child will be terminated if it's an exception, for example, right? That's how it works. But in this case, if exec succeeded, the old process is gone, right? It's kind of replacing the address space. It will never run again. In fact, exec doesn't return. It only returns when there is an error. If there is no error, it doesn't return. It just starts in a new process, in a new address space from the entry point.
But before we are executing ls, we are relocating the old process.
Yeah, and at this point, you have to be careful. You can panic, meaning maybe your system cannot handle this condition, and probably, but the idea is that you design everything so carefully that at this point you're not gonna fail. And the reasons for failure, modular, like, okay, you made a programming mistake, but assume that you didn't. The reason for failure is essentially just running out of memory in a memory allocator, or some other resources. But I think the only other resource which we're allocating was, I don't think we did anything. In case of fork, you will have to allocate a new process like proc-alloc or alloc-proc. And that might fail because maybe you ran out of like data structures to describe processes in the system. But in case of fork, I think the only error conditions is it's either the user provided the wrong argument, it's not really an L file, or the file doesn't exist in the file system, or the argument is pointing to some obscure memory location, right? And then I think the only other failure is running out of memory. Yeah. Okay. So we're good with this. When we understand that what now has to happen. So we switch the page tables. So, and we know how to do it. You have this function switch UVM, and not surprisingly, that switch UVM will just, will essentially will load the new, this process data structure has a pagedir pointer, and this function will load this pagedir into CR3 register, right? And after that, you're running on a new address space, and on this new address space, you will return from the interrupt, right, into main. And the last thing you do is you're freeing the address space. You're freeing the old page directory here, right? And I already explained that it's the page directory which describes the old address space. So if I ask you a question, how do you think you need to free it? What does it mean to free a page table?
Had to call one free method. I mean, we had to give back the pages to the kernel, and we had to give it.
Correct. So we have to give the pages back to the kernel memory allocator. So how do we do that?
We traverse the page table.
Correct. So what we do is that if we have a page table which contains a root page table directory and a bunch of leaves, right? We'll be just walking this page table from like I equals to 0 until I equals 1023, right? The last entry. Check if the entry is present, then we go to the leaf and we say, look, this is the physical address of a page which contains this memory, right? And this is what we want to deallocate, right? But even to deallocate this, what we need to do, we actually have to say, look, there is a pointer here, which is a pointer to the actual page, right? Maybe it's a process text, right? Or the next page might be pointing to the process. There will be a couple of pages for text, but eventually there will be a page for data, right? So you can do that, right? So and you say, okay, I have a physical address of this page, right? Because it's pointed from here. What you do is that you know that this page is mapped in your kernel address space. So you do this P2V address, right? And you get a virtual address of a page. And you return this virtual address of a page to the memory allocator saying, okay, we're done with this page. This page will never be used again until you allocate it again, right? So you keep walking these pages. At some point you say, look, there will be some empty spots here. By the way, when we're done with deallocating all pages in this leaf, you deallocate the leaf itself, right? Because you say, okay, this leaf is no longer needed. Then you move forward, you go forward. Some of these pages will be describing kernel memory. Remember, just like kernel. And you do the same. You just deallocate this page by page by page, right? Agree with this? And you deallocate the whole tree recursively. So it's kind of similar. So when you in C++, you say free, and the compiler just usually, if you have a recursive data structure, often the compiler can handle it for you. Like it will generate it and correct the structure. But here we write it by hand. And when we're done with everything, we just deallocate this page. Saying the page which was representing the page table directory is free again. Is free itself, and now we're done, right? Agree with this? Okay, and this is what exactly the code is doing. So let me just quickly show it to you for a second. So this is our address space. So the high-level outline is the walk with the page table and deallocate all pages mapped by the page table, deallocate pages that contain level 2 of the page table. So essentially like the ones which were. So first deallocate those pages, right, which are mapped by the page table itself, then deallocate the level 2, and then deallocate the directory, right? And this is the function which says dealloc UVM, which essentially says, please walk everything. And here's we're walking the page table and essentially do this free algorithm, which I was describing. Again, you don't want to waste a lot of time, but if you read through the source code, you will understand how it works, right? Deallocate the level 2 itself and deallocate the page table directory, right? And this is it. At this point, we essentially learn how to exec and create a new process, or like essentially replace the address space of a process, right? And really, to create a new process, we need to use fork. And fork is very similar to exec. So the logic is like all the primitives which we discussed inside exec while discussing the exec function will be used inside the fork. So essentially you create a new address space. It's just that this address space will be attached to a new process which you allocate as well. And you will copy the stack, you will copy the address space, right? Okay. Okay, so any questions about exec? No, exact. The process data structure doesn't change. That's the beauty of it. So if you had the proc data structure, you're not creating a new one. You're just saying, okay, my address space has changed. So my page table is now a new page table, right? And this was the old one. And you essentially just deallocate it. And this is the new one. But you continue running. So everything is the same. Remember, file descriptors stay open, right? So if you have an array of file descriptors here, they remain open. Maybe, I think the name of the process has to change if there's a name, stuff like that.
For the general register, we need to give a
But for what?
general register.
Okay, great question. So what happens to general registers? Tell me.
In case of fork, we will reuse the same whatever values we have in the parent. But in exact, we have to revert back.
Yeah, so what is that we want to do in case of exact? That's a good question. So imagine this is the address space, right? This new address space. Like we say this. Imagine we're executing ls. And there is a data for ls as well. This is text. This is data. If like exam was a question. What are the values of new registers after exec? Who can tell me?
What they were before you called functions on the internet, the interrupt returns to restore the state. Summarize it. So I guess actually, whatever.
That's a good question, actually. And to be honest, I don't know the answer. I mean, I have a guess, but I don't know the answer. But let me show you how we go about it. So at this point, okay, imagine you're like trying to answer this during the exam. You say, okay, really good question. So, but I don't know the answer. So what do? You start looking at the source code. And you say, look, we talked a lot about exec, but we never really say anything about the registers, right? And what you're saying is that in my diagram, because if there was a kernel stack here, which we used when we, like again, if we had the old address space, we did this int x40 here, jumped into the kernel, and the kernel saved to like stack segment ESP, stack saved code segment EAP, and the error code sometimes. And then we did the all traps and saved all the registers, right? Here, right? So you say, maybe we're going to reuse these ones, right? But you immediately start noticing that something is wrong here. Let me highlight what is wrong. So who can tell me what is wrong in this? If we just blindly reuse these ones, what is wrong?
You free the location of your old stack, and so your instruction plan is not out.
Yeah, so these two things are clearly wrong. So like maybe we have a new location of a stack because maybe the new process is much longer and the stack has to move somewhere and we allocated it differently, or we just allocated it, we saw it, right? So clearly this has to be set to something new. So this one has to be set to the entry point, like from the L file, and this has to be set to the location of a new stack, right? And not surprisingly, exec does it. So maybe I kind of like skipped over it, but it's there, right? But what about other registers, like the stuff which got allocated here or got saved here? What are we doing with this one? Okay, let's ask the question, do we even care about those values? Like we start a clean program. We only care about the stack pointer and instruction pointer because the stack contains the arguments. The other registers are not defined by the calling convention because all the arguments are passed on the stack, right? So logically, you say, look, they probably can be set to 0. In fact, if you allow the old values to leak, maybe you're leaking some sensitive information. Maybe it's a password which got accidentally, or part of a password which got accidentally saved in one of the registers, right? So your goal as a designer is to say, look, I probably will set these values to zeros or something like that, or some predefined values on this new stack, right? Agree? That makes sense. Okay, the question is, how do we do this? So let me show you this in source code. So if this is the implementation of the exec which we described here, remember we started with the name I, we started reading this name I return as a what is it called? inode pointer. We started reading the elf header for the inode pointer. We did this loop for each program header entry, reading inode pointers and allocating memory for them. We said, okay, we allocated the 2 pages for the stack and a guard page. We pushed the arguments on the stack here inside the exec, right? And this is where we said, okay, remember, every time we enter with the interrupt, we create this drop frame data structure. I can make it a little larger for you. And this drop frame data structure points to the correct location on the stack, right? And so here, when we actually, this drop frame is still like valid, right? So what we did is that we said, okay, look, I will just reload the instruction pointer and a stack pointer, right? So that is done correctly, but we don't see anywhere, at least I don't see here, this process of zeroing out the registers. So I kind of claim, so unless I'm wrong, it's a bug, it's a security vulnerability in x86 system. We can, like, MIT moved to a different version now where they have a RISC-based version. I don't know if they patched it there, but it looks like that they don't zero out the registers. And maybe POSIX doesn't even require you to zero out the registers, but that's a channel. So because from the callie of the exec, this information propagates into the caller, right? So unless you you should dig through this source code a little bit, and maybe there is a line which zeroes out the registers, right? But maybe not, right? And if not, then it's a bug. I claim it's a bug, but we can double check with the GDB. It's a good extra credits, essentially. Put a breakpoint on this line and just check what the values of the drop frame are. And then you return from the exec, and I don't see where they essentially zero out the registers here. And that's the answer. So that's why it's exam worthy. So that's kind of the questions I might ask on the exam, to be honest. But good that it came from you. That's the question.
So for when we create pages, isn't that also a potential side channel unless we zero out the
Great question. So what's the answer? Who can tell me? It feels like a side channel, but I believe that x86 protects against it. Do you remember? Where? How do you go about it? So you're right. So you need to set pages to 0, but I believe that in most cases, at least the ones which I've seen, it does. So here, if you go to this, what is it, alloc UVM, not the best way to navigate the source code, unfortunately. You probably get a better way. Let me just clean so we don't have a cleaner build. So here, when you do alloc UVM, they actually set them to zeros, at least here. You also can allocate a page for a page table, like a page table directory or a page table. I think they do set them to zeros. So that one they handle. I mean, I found a couple of bugs in x86 when I was looking at it like over the years. That's a new one. I didn't know that one. No one ever asked that question. It was fun because they used to patch the bugs in this version. I'm not sure they do now, but we can submit a patch. They probably will, because they might maintain this version as well. But let's check. So whoever does it first gets extra credit. Submits a patch to the MIT. Okay, I'll give extra credit to everyone. So like just let's do a group patch since it's a group exercise.
Is there any case we only allocate partial entry or partial directory?
Partial directory for what?
Just like you mentioned, and if you want to allocate that, and we just allocate level 2 and the whole directory. This sounds inefficient. I mean, not flexible.
What do you mean? Like, what are you trying to achieve? So, or what kind of a performance bug you're trying to fix? Are you talking about when we do this dealloc the address space? This one, dealloc UVM?
Yeah, and we just work the whole directory. So we just drop the whole directory and all the page entries.
Correct.
By the directory.
Correct.
Just don't want all of that.
Maybe let's take it offline and then I will answer. I don't understand the question still, but ask me after the class and I will try to understand with you what's going on.
Okay.
Any other questions? Good. Okay, so done with exec. Fork is similar. Again, my illustration, tiny illustration here was to, again, there is sometimes a correct way to do something, and you need to have an intuition about what's correct, what's incorrect. Then you verify against the source code. MIT source code is pretty decent actually, so there are not many bugs, and so you can usually like learn from how they build things. But sometimes they also have errors. Okay, cool. Done with fork. So now let's move to the next lecture, which essentially will explain us how we switch from one process to another. And that's kind of exciting because, again, so low-level details of the context switch are, they're usually exciting. So if you understand them, you can build a lot of interesting things. Okay, let's start with a little bit of recap, right? I'll ask you a question. So at what point the operating system might choose to switch from one process to another? Well, that's an easy question, so you should answer.
On a clock interrupt.
On a timer interrupt. That's one reason. And this is the one which I was kind of mentioning all the time. There are additional reasons. There is an explicit system call, which is called yield. That's just allows a process to be a good citizen. Maybe a process says, okay, I'm done for now. Maybe I'm waiting for something. Just wanna maybe run every so often or something. And so yield is one way to say, okay, I don't need the CPU anymore. And sometimes when you do I/O, so essentially you do a discrete, and the operating system, your program jumps into the kernel with the read system call, and inside the sysread, and we will cover the file system in a week or two. Like at some point, you configure the disk to say, okay, here's the region of memory where you have to perform the read, but I know that it will take you 10 million cycles, and so waiting for these 10 million cycles doesn't make sense because the user notices like there's like a glitch, and sometimes you see it on your system. I see it a lot on Linux because Linux doesn't have a very, very good scheduler. I mean, what is good here? It's a good question. But at some point you say, look, instead of waiting for this read to complete, let's yield here as well, right? It's kind of logical. And some other process will get to run, maybe 10 other processes will get to run. And then later on, when the disk is done, the disk will raise an interrupt, and we will process the interrupt handler, and this interrupt handler will switch back to this process, right? But okay, so we got the intuition. So timer interrupt, explicit yield, and I think at x86 there is no yield, but there is something like a wait, saying that I can wait for some number of clock ticks. But those are the reasons, right? Okay, that's cool, right? We have the intuition. Let's quickly take a look. Let's take a look. Let's take an example of a timer interrupt, and let's take a look at it, how it works, right? So I'll skip this assembly part for now, but we'll come back to it in a second. So this inside this trap function, right? So we're familiar with that. Remember this trap frame as the pointer to the stack, which is to the current stack where all the registers are saved. We say, okay, what's the interrupt number? It's number 32, so it means it's a timer. We will increment the number of ticks here just to say, okay, we will keep counting how many ticks are happened since we booted the system. We wake up all the processes which are waiting on the timer. And later on we say, okay, if we have a current process and the process is running right now, and the trap number is a timer interrupt, we're going to do a yield. And this yield will switch us from one process to another, right? And what do you think should happen inside this yield? So what x86 is doing, it invokes it acquires a lock. It says, okay, I know that this process was running, so we will leave it in a runnable state, meaning that it's ready to run again if the scheduler decides to run it again. Goes into the scheduler, right? So essentially this is some part of the system which decides which process has to run. And at some point, this scheduler makes a decision and makes this switch, making the switch from the current process to another, right? To the other process which it wants to choose, right? If I ask you a question, what do you think needs to happen inside this switch function?
Switch all the registers and use that.
Correct. So you say we want to switch the state of the current process from the state of the current process, which means register, and what's more important, even stacks, right? And essentially switch from the old one to a new one, right? And if I keep this analogy of boxes, essentially, if you say maybe I was running here doing some computations in the loop at user level in this process, right? User. The timer interrupt pushed me into the kernel. So this is a timer. We started executing like vector 32, like all traps, sorry. Then got to the trap function, then got to yield got to scheduler got to switch, right? And if this switch packs all the state in the process in some kind of a box, and it's up to us to design how this box yields, or how this box looks. And we have another process which had a similar past because something like that happened to that process in the past. So maybe it was preempted with a timer interrupt, or maybe it yielded explicitly yield inside the IO, right? But clearly we say, look, clearly something like that happened to this other process in the past as well. And so if everything is packed in those boxes, if we just at some point just switch from one box to another, then supposedly we should, that's the switch, right? And we just will take a look at how we pack all the state and do the switch, right? In just the next, whatever, 40 minutes, which we have today. But the high level idea is clear, right? Right? Okay, so if I ask you a question again, so what is the state of this? What do we have to pack in those boxes?
All of the registers.
All of the registers. What else?
The process structure. Just the one we put a runnable state into it.
Yeah, so the proc is a data structure in a kernel. Okay, agree. What else? It has like file descriptors here, right? Reachable from here, stuff like that. Page table, page there, reachable from here, right? Just drawing most important state so we understand where things are.
I was gonna say CR3.
CR3 is part of the switch, right? you're right. So when we're switching, we should probably switch CR3 because we clearly want to go from one, like CR3 was pointing here, so we have to point to this address space of the new process, right? So this is proc2, this is proc1, right? And this will have page there pointing here, will have its own file descriptors pointing like to whatever, to some kind of files, right? That's kind of, I mean, I'm pretty sure this is more or less it. But when you say registers, what are those registers? Can you elaborate a little bit?
Well, of course, we have the standard registers, EAX, EBX, and so on. But I was just asking myself this: what about the floating point registers and those kind of things?
You will handle them similarly. There are some tricks how people optimize handling of floating point registers. x86 doesn't support floating point operations at all, so they don't even initialize them. But I wanted to emphasize the following. So remember, when you were running in your wonderful infinite loop, which you designed as part of the high performance computing exercise here, obviously there were some registers here like EAX, EBX, and so on, right? Do you have to care about those guys when you do a switch? User level registers. You do or you don't?
I suppose we would not, because they were saved as part of the switch to
the kernel, correct. So when we had an interrupt, the interrupt actually saved all the user space registers, correct? And remember, we also, like your ESP, which was here, which was pointing to some user stack, is also updated. So right now you actually have a stack, and this ESP is actually points to this stack, and all these registers here, user registers, are actually saved on this stack, right? So I just wanted to make sure that we understand that the user state is already saved on the kernel stack. Remember, there are two stacks, like user and the kernel. Right? Agree with this? So, and those user registers are saved there. So we don't even have to care about them, right? We only need to care about the state which was like from this interrupt to the switch function, which was unsaved, right? I also wanted to make sure that we understand that the page table itself is accessible from the proc data structure. File descriptors are accessible from the proc data structure. So roughly speaking, if we later have access to the proc data structure, we don't have to care about the state either, right? Agree? Like as long as there's, imagine, as long as the operating system maintains a list or array of all processes in the system, at some point it will come back to this process again when it's time to run this next process, and it will be able to access the page table, the file descriptor, everything, right? Right? It seems that we only have to care about the stack, the current stack, like, and the current registers inside the kernel, which are not saved, right? It just, again, I wanted to give this high level overview. So if you just save these two, like unsaved registers, like and a stack, then you will be fine, right? You have to switch between those. And further, just another thing which we will, like, which we will choose as a design choice, we actually will save the registers themselves on this stack. And at some point we will care only about the stack, because the stack will be our box, the box which I was drawing on the screen. So everything will get saved on a stack, and we'll be just essentially switching between two stacks. Let's take a look at how it works. So this, just the reminder, this is the process data structure, right? The page directory is a field. The kernel stack is a field, so it will be accessible. It's a page, so the current value of the stack is not really saved, right? But the rest, the other state of the process is actually saved in this process data structure. But let's take a look. So I have a couple of slides to kind of prompt this discussion, but we already did it. Let's essentially take a look at the timer interrupt and decide how everything gets packed in those boxes. Now, in more details. And the details are at the level of assembly, as long as I can move to the next page. Next. No, no next for me. Let's wait for my slide deck to come back. Oh, slide deck. Okay, cool. So this is what we were doing. So we were running. Sorry, I just pressed a couple of buttons back and forth. You see this is my scheduler trying to run Zoom and OpenOffice at the same time here. So it's struggling. You were running at user level, right? Again, your infinite loop here, which I was using as an example. You had some stack pointer, some instruction pointer, right? Imagine timer interrupt shows up, right? So you have those helping data structures which allow you to switch from the user to the kernel. Just waiting for the slide deck. Just a second. So timer interrupt, you have IDT, you have task state segment, right? So essentially what you do, the hardware saves this 5 things on the kernel stack. You locate this kernel stack from the TSS, right? So there will be a pointer to the kernel stack in the TSS. Inside the interrupt descriptor table, taking the number of the interrupt, you say this is position number 32 in this interrupt descriptor table. You take the code segment. Code segment is essentially as a pointer in the GDT. You take the segment which has a privilege level 0 and the handler pointer, which points you to the address space of the kernel, which is an entry to the interrupt handler, which is vector 32. This is how we generated it, right? So just a reminder how interrupts work. And this is the first code which you execute in the kernel, right? So you switch to this kernel stack. The 5 things are already saved by the hardware. You push this 2, you push the error code because the interrupt doesn't push the error code. Hardware doesn't push the error code itself. You push the number of the interrupt 32. You jump to all traps. This is how the stack looks like, the kernel stack looks like right now. So EAX user values of EAX, EBX are not yet saved, right? So this is what you do next. Inside all traps, you said, okay, we will first save all this code stack and data segments, and then we will switch to the data segment, FS and GS segments in the kernel. This is kernel data. We will use push all to save all the general registers on the stack. And then we will enter the C function trap, but the stack will look like this, right? So 5 things saved by the interrupt hardware, 2 things which we push from the vector 32, segment registers and all general registers are pushed inside the old traps, right? So we saved all the state of the user program, right, at this point. And we're running inside the kernel. Again, got to this point when we react to the interrupt, got to the yield, and executing inside the yield, got into the scheduler. We say, let's invoke the scheduler to make a decision. And at this point, scheduler says, okay, I chose the process to run. I will start the context switch. And let's take a look at this switch function. This is how the stack looks like when we invoke the switch function. Remember, the switch function has 2 arguments, right? So these 2 arguments are pushed according to the calling convention on the stack, right? So there were 2 arguments. So one was called the context, a pointer to the context, and this is the pointer. And the second argument is the pointer to the scheduler, or like, as we'll see later, the context of the scheduler. So this is where we were going to save the old state, and this is the new state. Like, or if you like the box analogy, this is the new box. So we're switching from this, from the old process. So this is the current process which we're running in a system, right? And this is what we're switching to this CPU scheduler, to the scheduler running on the current CPU. And this is the diagram which essentially describes how the state looks like, right? So this is the kernel stack of the currently running process. This is the pointer to the context field of the proc data structure. And I'll give you a hint. So this field point to this stack after we save additional registers, some unsafe state here. And not surprisingly, this is the pointer to the stack or the new box to which we're switching, right? So this is the process and this is the scheduler. right? It will become clear in a second. But we agreed that the state might look like this right now, right? Okay. So we entered this switch function. Again, the main observation here is that we're packing into two boxes. In practice, the boxes are stacks. So we pack everything on a stack, save all the state of the old process on this stack, and switching to a new stack. And this is what the switch function will do. If I ask you the question, like we talked a little bit about it, right? So we know that the user registers are saved on the kernel stack as part of the interrupt transition. We invoke this switch function with two arguments. If we were switching from this process 1, which got preempted with the interrupt, what is left unsaved? Like, again, exam-worthy question, but as a systems designer, you need to answer or try to answer. Well, remember, there is this process data structure. Imagine we have an array. x86 has an array of all processes. And this entry in this array is a proc data structure, which corresponds to the currently running process P1. So it has a pointer to the page table. So we don't really need to do anything. The next time we will come to the end, like this array is a global variable. The scheduler itself, and I explained what the scheduler, the part of the system which decides which process to run, it just essentially says, okay, I will take a look at this entry. Is it ready to run? No. I will take a look at this one. Is it ready to run? Yes. Okay, I will switch to this one. Like, imagine this is the process which sits here. We only have 3 in the system maybe, and this another process which is ready to run, and it will be our new process, right? So our new process which we choose to run, and it will have a pointer to the page table here, right? So there is no really need to save the page table, right? We already have it around in the proc data structure. I wanted to make sure that we understand it, right? Agree with this? So back to this. So what kind of state do we need to save inside the switch function? Okay, let me ask the question again. What is already saved? I claim user registers are saved, right? As part of the interrupt transition. So we're running in the kernel. We have a kernel stack. Kernel stack registers. What are those? So we have this stack here, right? Kernel stack on which we're running right now. So this is where we saved everything, like trap frame. And this is the current ESP is pointing here, right? But we're trying to call a function. If we call a function, what state is unsaved, really? Is not yet saved. It's back to the calling convention.
We need to update ESP and DSS, right?
We will do that as part of the switch. That's correct. Okay, what I'm claiming here is that we don't even have to save all the registers inside the switch. We only have to save the callee saved registers. Because if the register is a caller saved register, then the caller code is already pushed it here on a stack. For example, I don't know, what is the caller saved register? Do you know which one? Let's say EAX, right? It's already pushed as part of this. Like, the compiler generates correct code. So before even the function is invoked, this register will be saved. So you really need to save the callee saved registers, because you say, look, after the function returns, those registers might be changed, right? And if you want to restore them inside that function, inside the switch, you will save them, right? You have to save them. So you have to write this function in assembly, right? Because everything else is already saved. Like here, there might be your EX register, and it will be restored here after you return from this switch function, right? Okay, there are not that many call safe registers, right? So EBP, EBX, ESI, and EDI, right? And this is exactly what this switch function is doing here. So it took two arguments, right? So these two arguments are on a stack. They put them temporarily in these two registers, which are available because those are caller safe registers, right? So you say ESP is, well, let's put it temporarily in the EAX and the other argument in the EDX, right? And then you save the call safe registers on the stack by pushing them on a stack, right? And actually, so the layout of how you push them matches the layout of the data structure, which is called context, right? So you say in the reverse order, obviously, right? So you say my EAP is saved on the stack as part of the call switch function, right? So it's on the stack at the very top of the stack. Then EBP comes next, then EBX, then ESI, then EDI, right? And after that, I claim that after that, so after this last line, so here, all the state of the process is saved on the stack, right? We just pushed everything on this kernel stack. And at this point, what we need to do is we just simply switch stacks, right? So the main trick which x86 is doing is that it packs all the state, right, on the kernel stack. So if this is the process P1, which entered the kernel with int 32 timer interrupt, right? And this is the kernel stack. We first saved everything was like on a trap frame. And the last registers were saved here. This is the call saved registers, which was saved inside the switch function, right? By pushing them on a stack here, only 4 of them, right? And I claim that at this point, the state of the process is completely saved. The only thing which we need to remember is the position of this stack. So the current value of the SP is still unsaved, right? Because it's in the register, right? And we don't know it, right? But essentially what the x86 is doing, it says, okay, the switch function will be, these two arguments which we passed will somehow represent two stacks, and you will save the CSP as well, and then you switch to this new stack. And all the state will be already saved on this stack, and you start returning on this stack, and we'll start running a new process, right? Let's take a look at how it works. So to represent this last registers, the x86 uses the context data structure. So essentially, remember, if you have a process field, there will be a pointer to the something what is called struct context, right? And we just had it on this on a slide. It only has 5 fields, 4 registers plus instruction pointer, right? And when we entered this switch function, we passed the address of this field. So essentially, address of this field, right? Of the currently running process. And what we're doing in this function, since we say that, okay, this is the context, this is the current context, we just saved it, right? So this is the return value, and this is this 4 registers. We'll just update this field to say it points to the top of the current stack. This is how we save the last bit of information, right? And is that clear? So because imagine next time we come to this process, maybe an hour later, trying to execute it, we'll look at the context field. We say, okay, it points to some memory location. We know the layout of this memory location. We know that this is the top of the stack. And we say, and it's in a specific format. So we'll just restore those registers from the stack and just start returning. And at this point, those return addresses will at some point lead us back here to user level. Is this high level insight clear? No. It's a little involved. So try to ask a question.
Are you saving ESP in DSS table or?
Inside the process, inside the proc data structure, you will have, remember, I glanced quickly over this field. There is a kernel stack field. This is where the kernel stack is saved. So every time we will be switching from one process to another, we'll set the TSS field to point to this k stack plus 4 kilobyte, because we want to point to the very top of this page. So, but this kernel stack is already saved. And when we switch, you won't even do that most of the time, because no, you'll do, but then it's only to prepare for the next interrupt, to be honest.
Initially, we were looking in PS table, right?
Right. But only when we're already in the user level. When we will be switching back to this process, we'll be in the kernel. So we will pick up this context pointer, which will lead us here, and we say this will be the stack of the current value of the stack of the. So our ESP in the kernel will be pointing exactly here, and that will be enough to start restoring the state. We'll see in a second. But essentially, the high-level story here is that we packed all the state on a stack. And we know that previously someone else packed all the state of a process to which we're trying to switch, or specifically to the scheduler, on another stack. And we essentially, at this point, we say, look, we took this other stack as a second argument, and we will be just switching between them, right? Okay, let's see how it works. So we saved the last registers here. Now we're switching stacks. Remember, the value of this context field was passed as one of the arguments. So it's a pointer to a pointer, meaning that inside the proc data structure, there will be a context field and a pointer, so which is a pointer, so it points somewhere. And we, inside this EAX register, we save the address of this cell. So whatever it is, right? So this is the adder. And so if we use this adder, we say, okay, please put the ESP, current value of the ESP in the EAX, meaning that ESP will be saved here, and it will be pointing to this, to the current context, right? So essentially what we've done is we are establishing, let me just show you which pointer we are establishing. Let me clear everything on this. We are establishing this ping pointer, right, with this move instruction, just essentially assigning something to this field, right? So right now we know this location as the value of ESP, and that's why we move the current value of the ESP into this memory location, right, to save it. Okay, so we've done this. Then we're saying, okay, we've done with the old process. At this point, we don't want to hear about it anymore. But you say, okay, what is it we're going to run next? And we say, okay, we're going to run next whatever was passed to us as an argument. So remember, this was the first argument, which allowed us to save the state of the the current process. And the second argument is essentially say, okay, it's a pointer. It's a pointer to the stack, to some other stack, which we saved before. And we're going to switch to this stack, right? So if right now our ESP still points to this old stack, what we want to do is that we say, look, we will set ESP to point to this new stack, right? Why not? Because then we will start restoring state. And this is exactly what the second instruction here is doing, right? So what it does here is, sorry, it says, okay, my new stack is passed to me as an argument. We saved it in the EDX register. So if we load EDX register in the ESP pointer, that's what we want. So what we essentially established is with the current value of the ESP register points to this new stack, right? So we did the switch between the two stacks. That's what we've done. We remembered the old one in the context field of the process here, and we switched the ESP to something what was passed to us as an argument into the switch function, right? And at this point, we're running on a new stack. And apparently, the stack is a very powerful thing. So it remembers the past, right? And if it remembers the past, we can return to that past. And so if something happened in the past, if someone in the past switched away from this stack to us, then we can switch back, right? So, okay, cool. So we saved the old stack of P1, loaded the new stack of P2. and we say, look, if this new stack is well formed, and we say that the context data structure is on the very top of that stack, we will start restoring the same registers, right? So we saved EDI the last, so it's at the very top of the stack. So we restore EDI. We saved ESI before that, so we restore ESI, and so on, right? EBP. At this point, we, 4 fields, 4 registers, 4 quality saved registers are restored. At the very top of the stack is what? A return address. And so that's why we can invoke a ret function, ret instruction, right? Which will pop this value, EAP, from the stack, and we will return somewhere. So where? Who can tell me where? Where is that we're returning? Yeah, back in the day, someone called the switch function. We don't know who called it. Maybe it's a different call path, right? But we're returning from the switch, right? We're returning to this, like on that stack, the switch was invoked. So we return here, right? Okay, that's good. But at this point, we should pause for a second. And I said, okay, we came to this switch function from process 1, which was preempted with an interrupt. And we did this dance here, saved all the state, did the switch. So this stack is essentially, so we have a process data structure, proc, for this process P1. The context field of this process data structure is pointing to the top of this process kernel stack, right? We did the switch, and we do the ret, and we say there is some other stack here, right, on which we're returning. And the question is like, what is this? What did this stack belongs to? And one thing one way to build the system and to say, maybe it's a stack of another process, right? And that's kind of natural, but that's not how x86 does it. It's a stack of something what is called a scheduler. Let me explain what it is. So it's not a process, it's part of the kernel. It's running in the kernel, but let me explain how it actually came to existence. Remember, we don't remember, we never learned it yet, but this is how it works. The main function, remember, we boot into the main function. The question is like, how does the main function ends? It ends with this MP main function. MP stands for multiprocessor main. So this MP main is invoked on every processor in the system. I never explained how we initialize other CPUs, but we do. So if you have a multiprocessor system, I will come back to it. So this MP main runs on every processor in the system. But this specific example, it's our boot processor. That's the one on which we're booting, right? This is the one which puts this string when x86 boots. It says, okay, CPU 0 or 1 booted, right? It initializes the interrupt descriptor, table register, and enters into something what is called a scheduler, right? So we end the boot. On every CPU, we end the boot with the scheduler function, which means that, remember, on this, when we were executing main, we allocated some kernel stack. And the main ran on this stack, right? And we ended with this scheduler function, which also uses this stack, right? And this is the case for every CPU, right? On other CPU, there will be another stack, but the story will be very, very similar, right? So the scheduler function runs on this stack, right? So on each CPU, the kernel will create a stack for itself, right? On which it boots. And what the scheduler function is doing, it actually tries to pick a process to run. In x86, the processes are represented as an array. So it's simply an array, and it might have an empty slot, which means that it's available, or a slot which contains an actively running process, the process which was already created, right? And what we do here is it's an infinite loop. And what x86 does is that, okay, I will try to go in order through this array, trying like incrementing the pointer, right? I check if the state of the process is runnable. If not, I will continue to the next element. If, however, the process is runnable, I will set P to the current process, and I will try to switch into that process. So this switch UVM essentially will take the page table, which is pointed from this process data structure, will load it into the CR3 register, will set the state of the process to running, and it will invoke the same switch function. But at this point, the scheduler on which you booted, you essentially will try to switch to this. Let's imagine we pick this process, right? We'll try to switch to this process, right? So this is where the switch function was actually invoked. And remember, we said we are returning to the switch function. So, and again, exam-worthy question. So we are actually returning. We'll come back to this line 2479. Clear? Because this is how we first switch into the process, right? We ran this process. Let's imagine it was proc something. This proc something was like running at user level, then got interrupted, then went into the kernel, went into the switch function, and the switch function switched the stack, and it switched back to this stack of the scheduler, and it essentially returned right here. Does this make sense? That's the past of the process, essentially. So the scheduler switched into the process, and at this point, we're switching back to the scheduler. And the scheduler is just the function which runs at the very end of the boot. It never exits because it's in the very, it's in the infinite loop. The moment you reach the end of the table, you reset the P to the beginning of the table and you go over again. The scheduling discipline is called round robin because each process will have a chance to run in a round robin fashion. Right? Does it make sense? So we specifically returned right here, right? And what happens next? Well, not surprisingly, let me just erase everything on the screen. We will say, okay, we'll switch back to this address space, to the kernel virtual memory, because maybe this process will get destroyed later. And we'll continue with this loop. So essentially, next iteration of a loop, we say, look, if P is not reaching the end of it, we'll do this check. Like if the process is runnable, we'll try to switch back into this process, right? Essentially, the context switch in x86 works like from process P1, you switch into the scheduler. Scheduler picks the next process, switches into P2, for example. P2 gets preempted with an interrupt, switches back into the scheduler. The scheduler says, okay, which one is to run next? Maybe P3 is not available, runs P4. P4 switches back into the scheduler. And scheduler says, okay, maybe we'll only have 4 in the system. At this point, it says, okay, well, I will switch back to P1 again, right? That's how it runs. Is that clear? But we now know how to switch between them. Yeah, it's a question.
What is the process variable here for PLC?
Which line?
The 2475.
So what is this process variable, right?
Yeah.
This process variable is a global variable which essentially points to the currently running process. It's a little bit more tricky, I think. Let's just quickly check. Because on each CPU, this variable has its private instance, and I never discuss how it's actually implemented. If I can, my proc. I don't want to spend a ton of time, but we'll come back to how it's defined. So essentially, in this specific case, I think in the scheduler, it just, hold on, I'm wrong. It's a local variable in the scheduler, right? So if I go here and go to the, I wanted to get to the scheduler function. So here, so proc is a local variable. I'm sorry. So it's just a local variable on a stack of the scheduler. So it keeps the.
What is the variable for in the for loop?
Why do we need this variable?
Yeah. In a for loop.
So look, I use a slightly outdated version of the source code on my slide. So back in the days, probably proc was the macro which allowed you which was expanding to something like on a current CPU, which is C. C is a current CPU on which the scheduler is running. So this is how you get it. So my CPU. You're saving the current process because later on, when you exit into the user, and at this point you don't have any state in the kernel, right? So the kernel stack is empty. If you want to come back to this process, you have to read it from somewhere, and you read it from this global variable, sorry, per CPU variable. And I will explain what per CPU means. Okay, 2 more minutes. Okay, so we boot into the scheduler picks the first process to run, it switches into it, we run for some time with the switch function. At some point, it gets preempted with an interrupt. We come back here to line 2479 because we return from this switch function, and we back into this loop, and we again like back and running, essentially picking the next process to run, right? So just to explain you a little bit of this machinery here, so we have an array of CPUs because the system can boot with multiple CPUs, right? And on each CPU, we have this CPU data structure, and it will remember the context of the current scheduler. So essentially, remember when we did the switch, we passed this, we did something like a current CPU, like C context, and we passed it as an argument to a switch function, right? So, and like when we inside yield, for example, right? So inside yield, we will know this C. C is this process data structure, which is coming from this array, and inside this data structure, there will be a pointer to the context. And remember, context is always the top of some kind of a stack, right? So in our case, it will be the stack of the scheduler on which we boot it, right? So this is how the kernel remembers it, right? And this is how it looks, right? So essentially, at some point, there will be, remember, first time we did something like call main, and this address, return address of main got saved on this kernel stack, right? This is the very first time we used the stack, right? Or even if we did a long jump to main, but I think we called main, right? And then we like called other functions, and at some point we called MP main, and we entered MP main function, and so on. So this is the pointer to this is the stack of the kernel on each CPU, right? And at some point when we said, okay, when the scheduler context switched for the first time, we passed this CPU scheduler as an argument. Remember, this is like from the process or the old process, and we said, and this is where this is the pointer to the field which will save the current stack, right? When we're switching from away, we essentially save all the state here. This is the box from which we're switching from. This is the field. We say, okay, remember this pointer, this stack ESP, and this is the stack of a new process which we are switching to. And this one we like proc context is the one which we're essentially switching to, right? Agree? Okay, so just the last minute. Essentially here. So if we booted, our stack look like that. When we first invoke the switch function, the arguments were passed like this. This is the first argument. It's a pointer to this context field. So the switch itself will add this four additional registers, which are Coli saved registers, and will update. Oh, sorry, like not this one. Pointer to this one. Sorry, let me just erase everything. So this one is a pointer to the context field inside the scheduler, right? And so essentially you will save this 4 registers inside the switch function and update this field. And the second argument is the pointer to the context field inside the process you're switching to. And this pointer essentially points to the top of a process stack right here, right? So this is the kernel stack, right? And if you logically, and we will finish next time, if you start returning on this stack, at some point there will be only these 5 things saved by the interrupt, right? And you can do something like IRAD and exit into the user level from this stack, right? Okay, let's finish this next time. So the finish the context switch. So, but we are very, very close. Essentially, you saved everything on one stack, ready to go, switching to another stack. Okay, thank you.
The one I want to ask is when we deallocate